Welcome to this brief and elementary overview of optical turbulence. This is meant to be a very basic and intuitive introduction to atmospheric turbulence and its impact on coherent and incoherent optical systems. Before we can talk about optical turbulence, we have to take a step back and review the basic definition of turbulence in general. In fluid dynamics, a flow is defined or classified as laminar or turbulent flow. To keep things very simple and basic, we say in a laminar flow, the fluid does not have any velocity perpendicular to the direction of the motion of the flow, and its velocity along that direction is uniform. The smoke of a cigarette is a great illustration. Closer to the cigarette, the flow is confined to a smooth cylindrical shape, and velocities along any cross-section have almost the same values. However, as the smoke ascends, it picks up speed, and the velocities are no longer uniform. This can also be seen in traffic flow. On a packed highway, all cars move almost along the same direction, same speed, and each stays in its own lane. Once we get to a turnaround, the flow becomes turbulent. Atmospheric turbulence results from the motion of the atmosphere surrounding the Earth. The atmosphere is composed of different elements that are distributed with different intensity with respect to altitude. As a result, different layers of the atmosphere absorb light differently and heat up differently. So we end up with hotter and colder layers of air stacked on top of each other, as we see in the figure to the right. In reality, the heat exchange process, although well understood, is a bit more complex than that. What concerns us here is not the actual mechanism, but rather the end results. The atmosphere becomes like a pot of boiling water, exposed to heating from the sun and the surface of the Earth. Therefore, air parcels, or eddies, are constantly moving, and the atmosphere is always in a turbulent state. This constant motion leads to breaking down of large air parcels, or eddies, to smaller and smaller eddies. The largest eddies are called outer scale, or capital letter L sub 0, and the smallest scale is called inner scale, or small letter l sub 0. Usually, we talk about eddies in frequency domain, with frequency defined as 2 pi over the size or the length of the eddy. And in the frequency domain, this defines the inertial range. The latter is bounded by the integral scale and the dissipative scale. This process is very similar to making brownies. First, we start from large blobs of brownie mix. Using the whisk, we add turbulence or energy to the system. The more turbulence we add, the smaller the eddies become. Eventually, the mix becomes homogeneous, or very close to that. From there on, any energy added to the system has to dissipate, therefore the dissipative scale name has to dissipate as heat. And that's when your mix starts getting really sticky. A major difference between the brownie mix and the atmosphere is that in the atmosphere, the large and small eddies are constantly being recycled. But why should we care? What concerns us is not really the sizes of the eddies, but rather their optical properties. Each eddy has a different size, different temperature, therefore different pressure, different density, and most importantly, different refractive index. The changes are minute, but once they are divided by the wavelength of optical waves around a micron, they become significant. That's particularly important for coherent imaging. Let us examine two extreme cases. The first one is a laser beam that's going through the atmosphere where the eddies are all larger than the radius of the beam. Let us consider the refraction of the first surface between two eddies. Based on the incident angle and the temperature difference between these two eddies, the beam will be stirred differently and ends up at different locations in the receiver plane. The pink and blue lines indicate two possible scenarios. In reality, there are unlimited scenarios. Now let us consider the other extreme. A laser beam propagating through the atmosphere where the eddies are much smaller than the radius of the beam. Obviously, each segment of the beam is going to go through a different eddy, and therefore each segment will acquire a different phase and propagation direction. As we see, the small scales have redistributed the energy and collectively have a diffractive impact on the whole beam. Let us look at a laser beam propagation through the atmosphere. Let us examine the intensity profile in the receiver plane. We can see the image is dancing around, and that's a refractive phenomenon due mostly to large scale. We can also see the redistribution of energy and the breaking down of the profile of the laser beam or scintillation. The red is a higher intensity and the blue is zero intensity. Of course, this happens because of the constructive and destructive interference of the coherent laser light. In incoherent imaging systems, the vast majority of systems, an incident plane wave, such as the green double lines, will be imaged as a single point in the focal plane of the imaging system. However, if the angle of arrival got tilted, like in the case of the two red lines, the image will be moved from the center accordingly. The atmosphere is constantly tilting and deforming the wavefront of incident light. Therefore, the image in the focal plane is always moving. In fact, smaller segments of the wavefront are distorted differently. And if we are able to image each segment separately, as shown to the left, we can see that these different segments of the image are not stretched uniformly, as shown to the right. And this is exactly what we do in adaptive optics when we try to correct for atmospheric turbulence. Here is how an image of a repeated pattern captured from about a mile away with a 14-inch telescope on a very cold day might look like. We can still see the image dancing, the stretching, and the blurring of the image. In a typical diffraction-limited imaging system, the image of a point source is never really a point source. Rather, an expanded or blurred spot in the image plane. The two-dimensional intensity pattern of this spot in the image plane is called the point spread function, or PSF. The objective of optical and system engineers is to make the PSF as narrow as possible to reduce blur and improve image resolution. The atmosphere, however, does exactly the opposite. It makes the PSF larger, degrading the image quality. The more turbulent the atmosphere gets, the worse the image gets. I hope you found this information useful. If you have any comments or suggestions, please let me know.